Hello everyone, welcome back to High School Tutoring. I'm your host Manny, and today we're going to be learning projectiles. So this is going to be a completely new topic that pretty much mixes kinematics and vectors together. So let's start with a couple equations values, and this is going to be multiple lessons actually. So in this little section we're going to be learning like some basics and how to find components and list values in specific. And then the next bit is going to solve mostly horizontal, and I'll explain that in just a moment. So let's begin with a little introduction. So here's some key values and here's some key equations. So I'll talk about why there's a y and an x and a y and a y and a y and an x and stuff like that, and why this has both. But you can get the rundown. V naught, our velocity is obviously a number of meters per second, and our distance a number of meters, and then our gravity 9.8 meters per second squared. That's just general, that's going to stay for a little while. And our time, obviously a number in seconds. And let's take a look at some equations. So we have some horizontal equations and we have some vertical equations. You can see this is a little confusing to look at because you see we have velocity x and there's none here. Then you have velocity y and it's all here. They're pretty much segregated to each other, and I'll explain that in just a minute. So let's open a little graph to represent how you would find how this would look if you were drawing it. So this is a little example graph. You can see we have 5 plotted points here. They're marked with these circles, and it's quite small, but it should be alright. So we have our gravity value, which is always going down, which is this. This could be considered negative, but I want to keep our velocity values positive, especially if you're solving for this, which we'll get into later. But that is kind of like what I mean. And so, alright, and you can see these components. You can see how as I'm going up, this y component here shortens. So you see it's much longer here when we just start, and it's much smaller here when we start. And then it's not here when we're at the top point. And then going down, and then all the way down. So we have our y component, and this is what I mean by gravity having this y value. It only affects the y. You can see the x component is the same throughout the entire equation, or through the entire parabola, as this is. All of these are going to be parabola equations. There's no denying that. But you can also see that as we're moving, time affects both of them. So you can see time is still pushing this to the right, obviously starting from here all the way down to here. And it's technically making this gravity actually have an effect on this y. And you can see there how it's changing. So you can see how these components are drawn. Obviously starting point, let's say we're throwing it up at a specific value, and we're throwing it to the right. Since there is nothing acting against this x-axis, against the x, it is consistently staying at whatever speed, which is why this parabola is symmetrical to itself. Imagine if there was a force that was affecting this and it was making it slow down, this parabola would look really weird. It'd be like a squiggly line. But this y value is affected by gravity, which is always going down, and you can see we're going against it here, so this is getting smaller, and then until nothing, and then we're going with it, so then it gets bigger. That makes sense. So yeah, that could probably lead us into why these have x values and these have y values, and why these are like this. When we solve for anything horizontally, aka this little x, or this little horizontal component, we never change anything because there's no g value. The only thing that stays the same is time, and yeah, that would just make sense like that. You can see here v final of x equals v naught x. That means that this stays the same no matter what. You can see here, obviously these lines are the same distance, all the same, and that's what makes this equation true. V naught x, v final x, if that makes sense. And obviously we have this for v naught y, or for v final y, and we have our v naught y, which is here, times gravity times time. So that would be like that, and that's just, well, we're doing horizontal mostly today, but for vertical it would be like that. And yeah, this introduction is kind of long, but we have the same equations that we've had since pretty much forever, really. And yeah, time is the only thing that affects both of these values, if that makes any sense. So let's get into a little bit of a little problem that we could start off with. So now we have solve for each component for the 2 instances of the baseball being thrown. The baseball on the right is thrown at 20 meters per second horizontally, and the one on the left is dropped. And our gravity is going to be 10, so we're going to ignore this 9.8. So we have this one here, this one on the right is thrown at 20 meters per second. So realistically, all we gotta do, we just select this and then go here, grab this. All right, and so this would just mean that all of these are 20. All of these values are gonna be 20, just like that. And so we see that this little horizontal line keeps going down as we start moving. That is the power of this gravity value. So if we look at it here, I'm just gonna change this color up. Let's go with this blue, why not? And you can see here, now we're going down. The gravity value, let's just do 10. Let's just represent it by this line. It's just going straight down just like that. And so yeah, and we have that value now. So if we take that into consideration, every single second of this ball moving, could see that this would be 0, this would be 10, this would be 20, and this would be 30. And that would make sense with this problem here, since our v0y is 0, and our gt, our gravity, is 10. Gravity is 10. Why in the world is this not drawing anymore? Oh wait, and our gravity is 10, let's say, so v final equals, and our gravity is 10, and our time, this would be 1, this would be 2, this would be 3, so I'll just do 2, just as the example. And if we just multiply 10 times 2, our v final is 20. And that should just make a lot of sense. That should make sense there. It's just taking the same equations. And then, let's see here, this line stays the same throughout the entire problem. So it is slowly dropping down, but it's still moving the same distance to the right. So that is kind of what this entire topic is about. We're just learning them throwing it to the side. I think next video, we're going to have them throwing it up and to the side. So we see like actual parabolas. But this is like if we were starting at the tangent point at the top. So now we have this value. And we'll keep it blue just to represent the y. And this one isn't thrown to the right at all. So remember, since x doesn't affect y, we can see that these stay separate from each other. This would just be the same as this. So we would have 0 up here, you'd have 10, you'd have 20, you'd have 30. It'd be the same thing as here. And yeah, just like that, it's pretty simple. That is all we have for this part, really. And that's all for this. And then I'm just going to skip ahead to the next part because I haven't prepped it. But yeah. Yeah, see you guys. I'll be in the next part. Okay, everybody, and we're back. So we're doing horizontal. So let's do a little bit. I'll do a little bit of explanation before I do anything. So our key values now. Most of them haven't changed, but some have. So gy 9.8 meters per second squared, same thing. v0x, same thing as it was before at a number meters per second. v0y is now 0. So that is one of our changed values here. And this value is now just meaning that we don't have a parabola like that, or obviously it has to be even. But now we have a parabola like that. So obviously this is not drawn very well, but we can see the idea that it's not starting to go down first, and then after gravity affects it. So we'll just have something named g, then it starts going down. So I'm just going to represent the rest of these points. Obviously we have dx same, dx or dy is the same as well, and time is obviously the same. So let me just represent what it would look like, what this would look like if you just drew it out. So we have this line going down, and then this line going to the right. This is dy, and this is d of x. So the d of x is how far away it is from the origin point. So this would be our origin point. I don't know. And d of x, obviously, we're stopping down here, so that would be what that is. And d of y would be how high it is above the ground, and that would be up here. And yeah, that would be d of y as the vertical, and d of x as the horizontal, obviously. And so and this point here, so we're just going to draw a little line. This is our v0 x. This is our initial velocity for our x, and yeah, that's how that would work. Obviously, g is always affecting force on the y-axis, which is why it goes down. So yeah, now let's evaluate our problem. So an airship is flying at 79 meters per second horizontally, so we know that our v0 x is now 79. Whilst being 500 meters above the ground, that is pretty obvious, dy, because above the ground, obviously it's our vertical. So yeah, the airship has to drop a package that's 800 meters away to a local town in Puerto Rico. So 800 meters away, that would represent x, our x value, so that would be d of x. How much time will it take for the package to get to the ground? So obviously now we know that we want to find time, and since time affects both, this would be our 0 seconds, and this would be our whatever our final amount, or whatever our final time is once the package hits the ground. So let's start solving. And I'm just going to explain a couple things before we go. We have 4 total ways to be able to find time in these equations. So we can find time using these 3 and using this equation. We only can do 2, and I'm going to explain why now. So since these 2 equations have some sort of value for v final, we don't have v final at all in this, or for the y value at least. Our v naught x would stay the same as velocity x, but we don't have a v final for y, or yet we could solve for it. So this equation and this equation get taken out of the equation, or get taken out of the problem. So we can choose from this or from this. I'm going to show both, but this would just be these would just be the 2 equations you would choose if you're doing a problem like this with similar information given. So obviously, since our v naught y is 0, we can cross this out, and our v naught x, this doesn't really change too much. But now we can just isolate. So obviously we would have to times 2, so that would be 2 dy, and then take that 1 away, and divide by g, so 2 dy over g, and then find the square root. That would be how we would isolate for t. So if we just draw that here, 2, and then we'll plug in 500 over 9.8 is equal to time, which is equal to whatever it is. So if we multiply 2 times 500, which we all know should be 1,000, so we just do 1,000 divided by 9.8. You get about 102, 101, something similar of that nature. And then we'll square root that answer, and we get about 10.1 seconds. So that is the first way to solve it. And now the second way is by using this problem. So just to isolate t, we have to divide, not subtract, by v naught x, and that would be how we do it. And so that would be 800 over 79, and that would be equal to time as well, which is equal to, let me just fix this bit a bit. All right, and then obviously 800 divided by 79 is also equal to about 10.1 seconds. It's a little more, but I think it's close enough. So yeah, that's really all you have to do to solve for this problem. But if we want to find our v final y, our velocity y, once it reaches, right before it reaches the ground, so we could use this problem. So it's obviously not listed in the question, but we'll do a little bit of extra work. Our vy is equal to v naught plus gt. Obviously v naught is crossed out, so it's just gonna be vy equals 9.8 times 10.1. So that's just gonna be how it is. So vy is now equal, so we do 9.8 times 10.1, and you should get about 99 meters per second. It's about 99 meters per second. You should get, I think, 98.98 exactly, but we're gonna round to 99 just for the sake of simplicity. So yeah, that literally is it for horizontal. If you wanted to find d of x, you'd find time first, and since we have our v naught x, you could just find that simply. And yeah, since we have a lot of options, there's plenty of ways you could solve for stuff. You could solve for d of y by finding time using this and then plugging it into here, or you can pretty much find anything. Obviously our g is just gonna be 9.8. That's gonna be given to us pretty much every single time, or you can infer that. But yeah, that's really gonna be it. I hope you guys learned something, because this is a new topic and it's just long. It's not really confusing, or it could be, but yeah. And good luck on your studies. So goodbye, everyone.